In this lecture, we'll talk about neutron stars, how they were discovered, and what can happen to a neutron star in a close binary system. Neutron stars are even more bizarre than white dwarfs. The possibility that neutron stars might exist was first proposed in the 1930s, but many astronomers thought the idea was crazy. We now have evidence that neutron stars do indeed exist. A neutron star is the ball of neutrons created by the collapse of the iron core in a massive star supernova. You may recall that at the end of a star's life, an iron core with the mass comparable to that of our Sun and a size larger than that of Earth collapses into a ball of neutrons just a few kilometers across. The collapse stops only because the neutrons have a degeneracy pressure of their own. Like white dwarfs, neutron stars resist the crush of gravity with degeneracy pressure. White dwarfs are supported by electron degeneracy pressure. In neutron stars, it's neutrons rather than electrons that are being squished. So we call this pressure neutron degeneracy pressure. The force of gravity at the surface of a neutron star is incredible. Neutron stars cram roughly 1.3 to 2.5 solar masses into a region of about 20 kilometers across. Matter is packed so tightly that a sugar-cubed size amount of neutron star material would weigh more than 1 billion tons, about the same as Mount Everest. A neutron star would fit into the Washington, D.C. beltway, but it would be a very bad idea to bring a neutron star anywhere near Earth. If you did, the neutron star's enormous surface gravity would quickly destroy our entire planet. It would squash Earth into a shell no thicker than your thumb on the surface of the neutron star. The first observational evidence for neutron stars came in 1967, when a 24-year-old graduate student named Jocelyn Bell discovered an unusual source of radio waves. Bell and her thesis advisor, Anthony Hewish, had built a radio telescope. Bell was looking at the data and found a source that was putting out very regular pulses of radio waves coming from somewhere near the direction of the constellation Cygnus. The pulses came at intervals so precise they almost seemed artificial. For some time, the phenomenon was half-jokingly nicknamed LGM, for Little Green Men. The pulsing wasn't due to extraterrestrials. It was discovered that the pulses were coming from a spinning neutron star we now call a pulsar. Pulsars are neutron stars left behind by supernova explosions. This is an image of Jocelyn Bell as a graduate student with her radio telescope. Her thesis advisor, Anthony Hewish, shared the Nobel Prize with another astronomer, Martin Ryle. Bell was excluded, despite having been the one to observe the pulsars. More pulsars were soon discovered within supernova remnants, including the pulsar at the center of the Crab Nebula. But what makes a pulsar pulse? As the iron core of a massive star shrinks into a neutron star, it spins faster and faster. The magnetic field lines within the core get all bunched up, and the magnetic field strengthens. The intense magnetic field directs beams of radiation out along the magnetic poles. If the neutron star's magnetic poles are not lined up with its rotation axis, the beams of radiation sweep around like a lighthouse. The idea is something like this. Like lighthouses, neutron stars emit a fairly steady beam of light. But we see a pulse of light only when the beam sweeps past Earth. The radiation beams sweep through space like lighthouse beams as the neutron star rotates. In order to see a pulsar, the neutron star has to be oriented such that its beams sweep past us. If we are seeing the system from overhead, for example, we won't be able to see the pulses. Therefore, we say that all pulsars are neutron stars, but not all neutron stars are pulsars. Binary systems in which both objects are neutron stars have been used to test Einstein's theory of general relativity. Relativity predicts that neutron stars emit gravitational waves, ripples of spacetime. This causes the orbits of the neutron stars to shrink and gradually brings the neutron stars closer together. Observations have found that the orbital decay does occur at precisely the rate that Einstein's theory predicts, giving scientists confidence that gravitational waves really exist. Pulsar timing was also used in the first confirmed discovery of extrasolar planets. In 1992, measurements showed that pulsar B1257 plus 12 has a slightly varying pulsation rate. An analysis revealed that the changes in the pulsar's pulsation rate could be explained by gravitational tugs of 3 orbiting planets. This was unexpected. It seems highly unlikely that planets could have survived a supernova explosion. Astronomers therefore suspect the planets formed after the explosion. Matter falling toward a neutron star forms an accretion disk, just as in a white dwarf binary. But a neutron star has a much greater gravitational field. Therefore, infalling matter will release far more energy. The temperatures get so high in the inner regions of the accretion disk that it emits X-rays. Close binaries that contain accreted neutron stars are often called X-ray binaries. Like accreting white dwarfs that occasionally erupt into novae, accreting neutron stars sporadically erupt with a pronounced spike in luminosity. Because these eruptions release energy, primarily in the form of X-rays, we call them X-ray bursts. X-ray bursts arrive from the ignition of helium fusion on the neutron star in a close binary system. Typical X-ray bursters flare every few hours to every few days. Each burst lasts only a few seconds, but during those seconds, the system radiates 100,000 times as much power as the sun, all in X-rays. That's all for the bizarre world of neutron stars, pulsars, and X-ray bursts. Take care. I'll talk to you soon.